Okay, so the object is moving down, and it's stopped in a distance of 1.85 meters, like that. And so the first step we're going to do is suvat it, right? So S is, we go down 1.85. The initial is negative 22 meters per second. The final is 0. The acceleration is what we want. And I would use v squared as u squared plus 2as, right? So a is going to be v squared minus u squared over 2s. So that's going to be 0 squared minus negative 22 squared. All right. Over 2 times negative 1.85. Okay. So basically it's just 22 squared divided by 2 divided by 1.85. So that's 130. The acceleration is positive 130.810, 810, etc. It's a repeater, right? And then this thing has a mass of 120 kilograms. So its weight is, there's an upward force on it. The weight is going to be 120 times. So I'm going to store that. And then 120 times 9.81. That's the downward force. Right? So now we've got an upward force. We got this guy is going to be a downward force, right? And then we go. So 120 times alpha A. And then this one's a repeater too. It's 297, 297. Right? And then of course I just add plus 1177. Whoops, 0.2. And I get F. Which is about 16,900 newtons. Maggie's got a question. Yeah. Okay. Did you make your displacement negative? Are we still working on this? Are we done? We're still working, okay.
I got 16,874.4.
Exactly right.
Should I round it up?
You'd say 16.9.
That was terrible.
Yes. Because it's moving down as it stopped, right? Right? I don't know what would happen if it moved up when it stopped, right? It'd be like, it'd be bad. I think it would be bad. Is anybody still working on this one? Class, if I could have your attention. So, this is, we could talk a little bit about rock climbing here too, okay? Talk about what we don't want to talk about, and that is falling when we hit a rope, okay? Okay, what is the effect of making this distance, the stopping distance, smaller? What effect does that have on the acceleration? Makes it greater. The shorter distance you stop someone in, the greater the acceleration has to be. Does that make sense? Okay. In this case, we figured out that the object weighs about 1,200 newtons. Isn't that right? This is about 1,200 newtons. but the stopping force is about 17,000 newtons. That's a factor greater than 10. Climbing ropes, I think the number they're shooting for is like 50 times your weight, okay, to stop you. Okay, so back in the day, and this is an interesting historical note, climbing ropes did not stretch. Okay, so if you stopped in 1.85 meters, that meant that somebody that was belaying you let the rope slip that far. Right? So they actually had different devices, different techniques. They wore leather gloves, and the idea was to let the rope run. If somebody fell a long distance onto the rope, you didn't want to just stop them and break them right away. Okay, you wanted to stop them in the biggest distance you could safely, because that made the acceleration less and the rope was less likely to break. And you were less likely to kill them with the rope, which is a distinct possibility, right? Nowadays, climbing ropes are dynamic, so they're actually like big rubber bands. They're designed to stretch, right? And so a climbing rope is rated for like 4 falls or 10 falls or something like that. And after somebody's fallen on the rope 10 times, it doesn't have any more stretch left. It's not going to break on you. It's just going to kill you. When you reach the end of the rope, you'll just stop so fast, right? So you got to be careful of that. And I'll leave you with this one little thought. Okay, there's something called a fall factor. And this has to do with physics and it has to do with elasticity. But the fall factor is the distance you fall. Okay, your fall distance divided by the amount of rope that can stretch. So not just the amount of rope you have, but the amount that's in the system that's available for stretching when you're stopped. Now the worst case scenario, okay, is that you are somewhere up a wall, you're up on a crack like this, okay, and before you set your first point of safety, you fall, and you fall twice the rope's length. The rope is 10 feet long, and you fall 20 feet. You fall past the belayer, and you slam onto that rope. That's a fall factor of, well, 20 feet divided by 10 feet of rope. That's 2. That's as big as it can get, because otherwise you'd need magic or something like that. It'd have to be like a Harry Potter rope that's long, I don't know, right? Okay, so that's the biggest it can be. The smallest your fall factor is, the better it feels when you fall. Now, it doesn't matter if you fall 2 feet onto a rope and you've only fallen 4 feet. That hurts as much, apparently, as falling 40 feet, right, onto 20 feet of rope or something like that. And here's the reason, okay? Because when you have the longer rope, you're falling farther, but there's more rope to stretch. So it's more stretchy. Does that make sense? And if you fall a shorter distance, you don't fall as far, you're not going as fast, but you have less rope to stretch. So either one is very jarring, right? It's kind of interesting. I'll put that, I know you guys are talented and gifted, so I'll let that percolate around in your mind, okay? Now,